Okay, so today we're going to talk about verifying trig identities. Verifying trig identities. And basically what this means is, or to give you an example problem of what you might see, you're given some trig equation. So secant x minus cosine x equals sine x times tangent x, for example. And you're basically trying to show that both of these sides are equal to each other no matter what theta you give or what x you give. And basically the way you show that is you try to manipulate one side of the equation so that it matches what the other side looks like. And one important thing to note here is that you're not trying to solve for x or theta. So not trying to solve for x or theta. And this is very important because it's something that a lot of students mess up is they'll solve it and then they'll have x equals some crazy trig function. And that's not what you're trying to do. All you're trying to show is that both of these sides are equal to each other. That's all you're trying to do. So all you have to do is manipulate one side so that it looks like the other. That's it. And then you're done. So this is kind of a difficult type of problem for many students. So I have some tips that might help some students out there get through these problems a little better. So some tips. So the first tip that I have is rewrite everything as sine and cosine. And this is really helpful because if you think about it, all the other trig functions are just functions of sine and cosine. Secant x is equal to 1 over cosine x. Cosecant x is 1 over sine x. Tangent x is sine x over cosine x. And so it's really easy to work with identities if you turn everything into sine and cosine. And also a lot of the identities that we already know, like the double angle identities, Pythagorean identities, they all include sine and cosine, so it's a lot easier to work with if you make everything into sine and cosine. The second tip that I have is to rewrite everything as a single function. Rewrite as a single function. And basically, the reason why you do this is, let's say you were given something like secant x minus cosine x, like how we did in the example before. Well, it's kind of hard to manipulate something like this on its own. So you always want to combine, additions or subtractions or multiplications together in any way you can so that you have one single fraction or one single expression. That way it's a lot easier to manipulate and it might fit itself into some identities. And the next one is start with the more complicated side. Start with the more complex side. So a lot of times you'll see something like sine theta equals, and then you'll have some crazy function over here. You want to work with this crazy function because you have a lot more to work with than you do with sine theta. Sine theta can branch out to anything, like most stuff, or like there's a ton of different possibilities you can take sine theta, but here it's a lot more direct and it'll be a lot more obvious what you can do with the more complex functions. So without further ado, let's go through some examples utilizing these tips. So the first example I'm going to do is this right here, is the one that we showed before. So secant x minus cosine x equals sine x tangent x. Now, the first thing I want to do is I want to see, is there a more complicated side? Well, there's not really a more complicated side. Both have two terms, but in this side we're subtracting, so I want to combine that into one single function. So we can rewrite secant x as 1 over cosine x, because that's one of our reciprocal identities. And then we have minus, we can say this cosine x is just cosine x over 1. And this is all equal to sine x times tangent x. A lot of the times when you're doing this, you don't have to keep rewriting the side that you're not working with, so just put it at the end. So now that we have this, we can basically combine these fractions. So the common denominator that we need is going to be something of cosine. So if we multiply this cosine x over 1, multiply the top and the bottom by cosine, we can have a common denominator. So let's go ahead and do that. So we have 1 over cosine x minus, if we multiply the top of this function by cosine, we get cosine squared. And if we multiply the bottom of this function by cosine, we get cosine x. And this still equals that. Now we can combine these fractions. So on the numerator, we have 1 minus cosine squared x. And on the denominator, we have a common denominator of cosine x. Now, if you recognize from earlier, we can simplify this numerator because it's a Pythagorean identity. So a quick side note, we know that sine squared x plus cosine squared x will be equal to 1. If we rearrange this, we get that sine squared x equals 1 minus cosine squared x. So you can see here we have 1 minus cosine squared x in our numerator. So we can basically rewrite 1 minus cosine squared x as sine squared x because of our Pythagorean identity. So this is equal to sine squared x over cosine x. Now, if we continue to the right here, we can split this up into two different functions. So sine squared x is basically the same thing as sine x times sine x, and this is all over cosine x. Now, we know that we can simplify this even further because we can take this as two different fractions. So we have this fraction right here, and then we have sine x over 1. So this will end up being sine x over cosine x times sine x over 1, or just sine x over there. And we know from our reciprocal identities that sine x over cosine x is just tangent x. So this is tangent x times sine x. And then what do you know? Here we have sine x times tangent x, and here we also have sine x times tangent x. So we've just proved that secant x minus cosine x is the same thing as saying sine x times tangent x. All right, so that was our first verification. All right, one more example. Let's say that we have secant x. So secant x equals sine x times the quantity tangent x plus cotangent x. Now, first thing I want to do is look for the more complicated side. So as you can see here, we're multiplying this quantity by sine x. So I think I'll work with the right-hand side because it looks more complicated. So secant x is equal to, well, first thing I want to do is just distribute this sine x because I don't like this quantity right here. So I'll have sine x times tangent x plus sine x times cotangent x. Now I want to simplify each of these multiplications into one single fraction and write everything in sine and cosine. So I know that tangent x is just going to be sine x over cosine x, so I can rewrite tangent x as that. And then I know that cotangent x is equal to cosine x over sine x, so I can rewrite it like that. Now I can combine these two or multiply out these fractions. So on the numerator for this fraction, I have sine times sine, which is sine squared x. And then on the denominator, I have cosine x times 1, which is just cosine x. Over on this side, we have sine x times cosine x as our numerator. And on the bottom, we have sine x times 1. Now, I know that I need to get a common denominator so I can combine these fractions. So I can multiply this fraction right here by time. So I'm going to multiply everything on this left fraction by sine x, because that's what our denominator is over here. I'm going to multiply everything on this right fraction by cosine x. So when we do that, we get sine squared times sine, which is sine cubed x, over cosine x times sine x as our denominator, cosine x times sine x. And we're adding that to, we know that our denominator on the right fraction is going to be cosine x times sine x. And our numerator is going to be sine x cosine x times cosine x. So that's just going to be sine x cosine squared x. All right, now we can just combine these fractions. So we get sine cubed x plus sine x cosine squared x all over cosine x times sine x. Now we can factor out a sine out of this numerator. So if I go up here, make a little bit of room. So sine x times what will give me sine cubed x? Well, that's just going to be a sine squared because I have one sine. I need two more sines to get the sine cubed. So I'll have a sine squared x over here. And then we pulled out the sine x from this second term right here. So all we're going to be left with is a cosine squared x. And this is all over cosine x times sine x. Now, if you notice, we have an identity that we can use. We know from the previous example that sine squared x plus cosine squared x is just 1. So all this stuff right here is just going to go to 1. So this is just 1. So I'm going to move my work over here. Now, since this is just 1, the numerator is just going to be sine x times 1. So we're going to be left with sine x on the top, and on the bottom we're going to be left with cosine x times sine x. Now you can see that the sine x's will cancel. So this will cancel and this will cancel. So we're just left with 1 over cosine x. And as we know from our reciprocal identities, 1 over cosine x is just going to be equal to secant x. So this is equal to secant x. So secant x equals secant x. And we've just changed this entire thing into, condensed it into secant x. And we've proven that secant x is equal to sine x times the quantity tangent x plus cotangent.